as we go through this video, here is a question that I'd like you to think about. We've discussed the one hot notation. The question is, can this one hot notation or representation be used to hold continuous data items such as heights or weights? Or is this only restricted to categorical data items? Do think over this question as we go through the contents of the video. Let's quickly take a look at some measures which are used to calculate the distance between a pair of points in an n-dimensional hyperspace. The most common way of calculating the distance between a pair of points is the Euclidean distance. This is the distance formula which we probably learned in coordinate geometry in high school. The Euclidean distance is a prototype for other distance metrics, so let's parse it. Given a pair of points x and xi, the Euclidean distance between these 2 points is calculated by first taking the difference between all of the coordinates of these two respective points. Notice here that each of these points could have any number of dimensions, so these are vectors that we are dealing with. We then square all of these distances and compute that sum, and finally calculate the square root of this quantity. What we get this way is the Euclidean distance, which is also the same as the straight line distance between a pair of points. For instance, in a two-dimensional hyperspace, this is the as the crow flies distance. This is what we would get if we were to apply the Pythagoras theorem to a couple of points. In other words, the Euclidean distance is equal to the sum of the squares of the differences between the x and the y coordinates. In our example on screen now, the Euclidean distance is the length of that line segment between the two highlighted points. While dealing with points represented in a discrete space rather than a continuous space, the L1 distance is a preferred metric. This also has various other names such as the snake distance, the city block distance, or the Manhattan distance. In any event, the idea is simple. The Manhattan distance corresponds to the number of grid blocks, either horizontal or vertical, that would have to be traversed in order to go from one point to the other. To make this real, let's consider an example. Let's find the Manhattan distance between the points 1, 0 and 5, 4. These are the coordinates of the two highlighted points. Here, the number of horizontal blocks which will have to be traversed is equal to 5 minus 1, which is equal to 4. This is simply the difference between the x coordinates of the 2 points. In the same manner, the number of vertical blocks which will have to be traversed is given by 4 minus 0. That's the difference between the y coordinates of these 2 points. Notice that we effectively calculate the absolute value of the differences. That is because the number of steps has always got to be a positive number. So calculating the L1 distances between a pair of points involves finding the differences between all of the coordinates of those points, converting all of those differences to their absolute values to get a series of positive numbers, and then going ahead and adding up all of those positive numbers. That sum is the L1 distance. In this way, we are able to add up both of these quantities and get the total number of blocks that will have to be traversed, which is equal to 8. The L1 distance between the points 1, 0 and 5, 4 is equal to 8, because that is the total number of steps that we will need to take in order to go from the other. Notice that this is only the case when our steps are constrained to be either horizontal or vertical. We cannot go in a straight line between the 2 points as we did in the case of a Euclidean distance. Next, we are going to turn our attention to a demo. This will involve actually coding up a digit recognition program in TensorFlow. We will do so using the k nearest neighbors algorithm. We will make use of the L1 distance in order to measure the distances between pairs of points, and we will end this implementation by testing the accuracy on some test data. Before switching over to the code demo, I'd like to outline the approach that we are going to take. The first step in our implementation is going to consist of accessing the images in the MNIST dataset. We will do so by using some TensorFlow libraries that are provided for this purpose. We will also be able to access these images in batches. Once that's done, we will set about actually calculating the L1 distance. Here we are going to need to calculate the distance between a test digit, that's what we are going to accept as input, and all of the training digits in our dataset. Once we have these distances calculated, it's relatively easy to implement the k nearest neighbors algorithm. We will predict the label for our test data on the basis of the nearest neighbors in the training data. Before we plunge into the implementation, let's also clearly understand the MNIST dataset, the attributes, that is, the feature vectors. This is going to consist of a set of images. Each image is represented by pixels. This is a standardized image where all images have 28 by 28. That is a total of 784 pixels. This is going to be the case for every image in the MNIST dataset. The labels associated with these datasets will correspond to one hot vectors. This is a new term and it's an important one. So let's please pay attention. What we have here is an image which clearly represents the digit 4. Now, the label of this image is represented in the form of a vector. That vector has 10 elements in total. Why 10? Well, because there are 10 possible output labels, the digits 0 through 9. So each label is represented using a vector which has 10 indices. Now, all of the elements in that index are going to be 0 with the exception of the one digit which it actually represents. So here in our 10 element vector, all of the elements are going to be 0 other than that with index 4. So the index of the one element which is equal to 1, that's the hot element, corresponds to the label of our image. In exactly the same manner, an image representing the digit 5 would also be encoded using a 10 element vector, but in this vector, it's only the fifth element, that is the element with index equal to 5, which is going to be equal to 1. This is the one hot notation which is used for representing images. Let's now turn back to the question we had posed at the start of the video. The one hot representation cannot be used to hold continuous data items. Think about it. The one hot representation of a digit, for instance, consists of a vector or a list with 10 possible values, out of which only one is equal to 1. The one element which is non-zero is called the one hot element. All of the other elements are 0. Clearly, this is only possible when we have individual columns for each possible value of our variable. That is not at all possible if our variable is continuous in nature. Continuous variables can take on an infinite set of values. Categorical variables can only take on a finite set of values, and that's why only categorical variables can be represented in the one hot form.